Striping is another technology that's central to most RAID technologies and most RAID levels, and it's of particular interest to us when we discuss RAID 5, RAID 6 and RAID 10. So first of all, let's take a look at how striping works with a quick few diagrams again. Again, we've got our write stream coming in. This time we have A, B, C and D, and this time the logical volume that our write stream is targeted at is not a mirrored logical volume but a striped logical volume, and we'll see how this differs from a mirrored logical volume in a moment. Again, we have our RAID controller. Could be hardware, could be software, makes no difference for us explaining the concept of striping. And finally we've got our back end again. We'll stick to 2 drives, it could be more, but 2 keeps the example quite simple. So let's look at our write stream coming in. First up, our A write hits the striped logical volume. This then is passed to the RAID controller, which redirects it to the first drive in the stripe set. We'll call that drive 1. This time there's no mirroring to our other drive. Next up, our B write comes in, hits our striped logical volume, hits the RAID controller and is passed to drive 2 on the back end. So far we've had 2 small writes. One has gone to drive 1 on the back end and the other has gone to drive 2. Now comes our C write. This again hits the logical volume onto the RAID controller and is passed to drive 1 on the back end. Finally, our D write comes in. It goes through the same process, hits the logical volume, hits the RAID controller, and hopefully we should understand by now that it will hit drive 2 on the back end. So we've had 4 small writes, evenly balanced across our 2 drives. If we'd gone for 4 physical drives on the back end, these 4 writes would have been evenly distributed across all 4 drives, with 1 write going to each drive. The theory should be clear, but what's the impact again on the all-important performance and fault tolerance? Let's cover off performance first. Striping, as we've seen, distributes incoming writes across all of our drives on the back end, effectively aggregating the performance of all of those drives. In our 2-drive example, if we assume that each of our physical drives was independently capable of 200 IOPS, then the logical drive created from them would be capable of 400 IOPS. That is the combined IOPS of both physical drives in the stripe set. This is a form of parallelism. But what about capacity? Striping has no overhead like mirroring does, so it has 0 capacity loss. But this lack of capacity loss or capacity overhead has an ugly side to it. Striping on its own provides 0 fault tolerance, and this should hopefully sound the alarm bells loud and clear. So striping can give us great performance and can aggregate capacity from multiple physical drives without losing any of that capacity, but you should absolutely be aware that striping on its own does not provide any resiliency or fault tolerance. Before moving on from striping though, let's cover some of the concepts fundamental to a solid understanding of striping, and believe me, you will want a solid understanding of striping for your CompTIA Storage Plus exam. Now then, there are a lot of concepts called out at the top of this slide, so we'll walk through a quick diagram to cover each concept off. First up, we have our RAID set. Sometimes we call this a RAID group. In our example, it's a 4-drive RAID set. This means that our 4 drives will be combined into a RAID set and used to provide persistent storage for logical volumes. These logical volumes could be mirrored, striped, parity protected, you name it. Now as we can see, each physical drive in our RAID set has been divided into 3 chunks. Each of these chunks is 4 kilobytes in size, and these chunks are created from contiguous blocks or sectors on the physical drive. So with a standard spinning disk drive that has 512 byte sectors, each of our 4K chunks will be made up from 8 contiguous sectors on the physical drive. The chunk is the fundamental unit in striping, and they can be larger or smaller than 4K, but 4K is quite common. Chunks are then combined into stripes. As we can see in our diagram, stripes are made up of adjacent chunks in a row. Our first stripe is highlighted and it comprises 4 4K chunks. This makes our stripe size in this RAID group 16K. 4 times 4K equals 16K. If our RAID group had contained 5 drives, each with a chunk size of 4K, our stripe size would have been 20K. And as we can see, our stripe depth is also 4K. So if a stripe is made up from a single chunk on each drive in the RAID set, and this is very often the case, then the stripe depth is equal to the chunk size. One last point to note, the term stripe width refers to how many drives are in our RAID set. So for our example RAID set, our stripe width is 4. Now maybe a quick recap and a chance to pause the lesson here and take a long hard look at that slide to help it settle in. Chunks are the fundamental unit of a stripe. They're made up from contiguous blocks or sectors on the underlying physical disk drive. All chunks in a row are combined into a stripe, and we saw how striping worked on the previous slide. The stripe width in a RAID or a striping config is equal to the number of drives in the RAID set or the stripe set, and the stripe size is the number of drives in the set multiplied by the chunk size. So in our example, the chunk size is 4K and the number of drives in the set is also 4. So 4 times 4 is 16, making our stripe size 16 kilobytes. Magic! But what does any of this have to do with performance? A couple of general rules to take note of. Firstly, if your I/O size is large, then go for a smaller chunk size. And conversely, if your I/O size will be small, go for a larger chunk size. Smaller chunk sizes tend to be around the 4 to 8K size, whereas larger chunk sizes can be 32K and upwards. Okay, so that's us done on striping for now. Let's move on to parity.